Hello everybody, welcome back to Embetronics. This is a STM32 bootloader series, part 4. Before starting this, let's recap the previous work. In our previous tutorial video, we have created two binaries for the bootloader and the application. We have placed these two binaries into the separate areas of the flash memory. When we reset the bootloader, it will come like this. Then, from the main function, we were calling the application's reset handler by using this vector table. It is like just giving control to the application. But in this tutorial, we are going to implement the bootloader and one PC tool that updates the application in the flash memory. Bootloader writes the application received from the PC tool in this flash area. Then, bootloader jumps to the new application. First, let's modify the application. In this tutorial, I have renamed the application's project name to Blinky. There are no major changes in the application. Just we are going to update the application's version number and delay. I have changed the minor number to 2. Previously it was 1, so that we can verify that the latest application is running. Then I have increased the delay to 5 seconds from 1 second. That's all. Build the application. Now the new application is ready. Let's move to the bootloader part. Now we are in the bootloader's project. We are using the user3 for debugging purposes and green LED for indication. This we have enabled already in the previous video, but now we have to enable one more UART for the data transfer and one button. The user push button is connected to the port C 13th pin. We are going to use this button to tell the bootloader to go to OTA mode. Please enable the GPIO PC13 as an input. We are going to use the user2 for our data transfer. So make PD6 as a user2 RX and PD5 as a user2 TX. Finally, enable the user2 in asynchronous mode. Then save and generate the code. Here I have changed the bootloader version's minor number to 2. Previously it was 1. All other functions remain the same. I have only added the OTA package receive functionality and writing it to the flash. I am reading the user button for 3 seconds. If the user has pressed the button, then we are starting the firmware update. See here, we are calling the ETX OTA download and flash function. I will explain that later. This function gets the firmware from the PC and stores it to the application's flash area. If that has been finished properly, then we are rebooting the microcontroller. Then it will run the latest application that we have flashed using this bootloader. If any failure during this process, then we are not giving the control to the application and just staying here. This is what I have added in the main.c file. And also I have added two more new files called etxotaupdate.c and etxotaupdate.h file. This etxotaupdate.h has macros like the start of frame, end of frame, ACK, NACK, structures, enums and many more. Before we see this, I will explain to you that how the host and STM bootloader communicates with each other using the UART. This is the host, basically PC, and this is the STM32. we have created our own algorithm which has OTA commands, header, data and response. Once we press the user button during boot, STM32 will be waiting for the data from the host machine. The host will send the OTA start command to start the OTA operations. The bootloader sends the response ACK or NACK. Assume that host received the ACK. Then the host will send the OTA header which has some information about the OTA package. Again, STM32 will respond to this. Then the host divided the full OTA package into multiple small chunks and transmit it to the STM32. Let's say the firmware size is 10 KB and the chunk size is 1 KB. Then it makes 10 chunks and transmits them one by one. The host will receive the response from the STM32 for each chunk. Once the host transmits everything, then the host will send the OTA end command to the STM32 bootloader. It will send the response for this command as well. If it is ACK, then the STM32 will start running the new firmware or application image that we have sent now. Let's see the frame format. This is the general format that we are following for this process. It has 1 byte start of frame, 1 byte packet type, 2 bytes data length, n bytes of data, 4 bytes CRC32, 1 byte end of frame. Based on the packet type, the data and data length will vary. We are using 4 packet types: command, header, data and response. We will see the example. If we want to send the OTA start command, it has to build the frame like this and sends it to the STM32 bootloader. This frame has the start of the frame, packet type as a command, length will be 1 for commands as we are going to attach only 1 byte command. Also, we will append the CRC32 and end of the frame. If the host wants to send the OTA end command, then all other things are same as the OTA start command. The only difference is the data and CRC32. The data has the OTA end command and CRC32 will vary based on the data. If you see the OTA header, all are the same. The packet type should be OTA header. As the header size is 16 bytes, it will make the length as 16 and append the data. Let's go to the data frame. Packet type should be the data and attach the data from 1 to 1024 bytes. For all the frames, STM32 will send the response, right? The response frame look like this. Please refer to the code. You will understand it if you are not clear now. Let's move back to the code. The main function calls the ETX OTA download and flash function. Here we are setting all the variables, resetting all the variables. Then we are clearing the buffer and waiting for the chunk from the host. If the received chunk is more than 0, length is more than 0, then we process the data. Otherwise, we will set the error and send the NACK. If we received the proper data, then we send the ACK. This is all about this function. Now, we will see how we are receiving the chunks. First, I am receiving the start of the frame, which is 1 byte. Then, we are verifying that. If the data that we received is not the start of the frame, then we are returning the error. Then, we have to receive the packet type, which is 1 byte. Once after that, we will get the data length. In the for loop, I am getting the data one by one to the data length and storing it to the buffer. Right after that, we will get the 4 byte CRC. In this tutorial, I am leaving the CRC as it is and not verifying the CRC. In the upcoming tutorial, I will add the CRC32 part. Finally, we will receive the end of the frame. Once we receive the chunk, we need to parse it and check what command or data it is. So, we have to process that. We will see what we are doing there. Here I am doing the initial check and I am checking that we have received the OTA abort command. This command can be received at any time, so I am checking it here. For other commands and data, I have one state machine. Using that, I am doing my respective operations. I have created few states. See here, ideal, OTA start, OTA header, OTA data, OTA end. Initially, we have to receive the OTA start command. We are checking that is this a command packet and it is a OTA start command. If that is true, then we have received the OTA start command. Then I will change the state to OTA header as our next frame is the header. If I receive anything other than the OTA start here, then I will return an error. If the state is OTA header, then we will receive the header and from the header we will get the complete OTA package size and its info. Then I will make the state to OTA data. If the state is OTA data, then we will have to receive the OTA package data in multiple chunks. Then we are writing the data to the application's flash memory. See here, we are unlocking the flash, erasing the application sector, writing the received firmware into the flash and locking the flash. Okay, now go back to the state machine. So we are writing the received OTA data into the flash memory. If we have received the complete firmware or application, then the state is changed to OTA end. When the state is in OTA end, we should get the OTA end command from the host. If we receive the OTA end command, then we are good. Here we have to verify the complete OTA packages CRC. Now I am not verifying it. I will add this feature in the upcoming tutorials. This is how we are receiving the data, processing it and storing it to the flash memory. And one more thing that I want to tell you. This is how the GitHub directory is structured. I have created the PC tool using the C program for Windows OS. Just go through the code. This code is used to send the application and firmware to the STM32. I have given some details in the README file. Check it out. This tool is tested with the Windows OS. If you see my code, I have used the do while 0 in most of the functions. Some people may think why the hell he put this unnecessary code. I don't want my function to return from multiple places in the function. I only want to return the function at the end. That's why I have used this do while 0 loop. Whenever I get an error, then I will break it from there and skip other process. Let's build and flash this bootloader. Don't flash the application because we are going to update this old application with the new one. I have the command prompt and serial terminal. Let me press the reset button. See the bootloader version. It is 0.2, new bootloader. Check the application's version. It is 0.1 and the blue LED blinks with a 1 second delay. We are going to update this application with a 0.2 version where we are blinking the blue LED with 5 seconds delay. Let's run the PC tool that we have created. This argument is the COM port number and this argument is the binary file location. Before running this, we have to put the controller into our bootloader OTA mode. Now the application is running, so press the reset button. After that, press the user button to go to OTA mode. See now, it is waiting for the data from the host. Let's run the PC tool. It has started flashing the new application. See now, the bootloader is 0.2 and the application is also 0.2. Previously it was 0.1 and now it is 0.2. Check the blue LED. It is blinking with a 5 seconds delay. That means our application has been updated with a new one. In our next tutorial, we will add other functions like toSlots, CRC, etc. I hope you enjoyed and learned something today. If you have any doubts or concerns, then please comment below. We will try to solve it. I have given my website link and the source code of these examples link in the description. Please check that also. We have many other tutorials like Linux device driver, RTOS, unit testing, C programming on our website. I request you to check that. Obviously, you will like that too.